I'm going to solve the GATE previous year questions from the chapter Heat Transfer in Flue over Plates and Pipes. So this is the first question. The impression of this question on most of the students, the first impression of this question on most of the students will be like this, that they will think that this question is quite difficult because of the heavy use of this equation and this equation, and a lot of variables are there. This is your chance to score extra 2 marks over those students because they will leave the question without even studying it. Now, most of the times what I have observed that the questions which have these kind of equations are quite easy or quite simple. There is only a single use of any concept, any basic concept. So let's read this question. The non-dimensional fluid temperature profile near the surface of a convectively cooled flat plate is given by this equation, where y is measured perpendicular to the plate. This is plate and this is the perpendicular distance measured as y, which has also been included in this equation. L is the plate length, A, B, C are constants, T, W is wall temperature, and T infinity is ambient temperature. Okay, thermal conductivity is K, and wall heat flux is Q double dash. Nusselt number, some equation is given, is equal to. Okay, so you can see that in this equation the value we have to find, there is Tw minus T infinity, and here also it is Tw minus T infinity. So what you can think that there is a use of this equation in this equation. Okay, this is the first observation. Second is, you can notice that in this equation there is K and L and Q dash. So you can also think that the heat transfer equation has also been related with this equation and this equation. Okay, so in these type of questions, whatever knowledge you have, just start solving the question, and most of the times, almost 100%, 100 out of 100 times you'll get the desired result. So let's start with whatever knowledge we have. Okay, so can I say that at this boundary at y is equal to 0, q double dash is equal to q double dash, that is heat flux, is equal to minus k del t by del y at y is equal to 0. Can I say this? Yes, I can say this, and this k will be kf because we have been given the wall heat flux is q double dash, and this will be dissipated here. But at y is equal to 0, q double dash will be equal to minus kf del t by del y is equal to 0, and the temperature profile has been given. So what you can do is you have to find del t by del y at y is equal to 0 from this equation. Okay, let's solve this. I'm you know I'm reorganizing this equation like this. Okay, now I'm differentiating with partial differentiation with respect to y, which gives me this. By L square. Okay, capital L square, and del t by del y at y is equal to 0 will be, I put y is equal to 0, what I'll get, minus tw minus t infinity, in bracket I will get b by L. Now put this term here, what you will notice that q double dash is equal to minus k minus b by L tw minus T infinity. Okay, when I rearrange this equation like this, q double dash L upon k tw minus T infinity is equal to b. This term and this term, are they same? Yes, they are same. So we get our answer is equal to b. So the trick is start solving this question. Start using your pen by whatever knowledge you have. Try to observe the equations, like which equation may be included in this, and then approach your question. Let's move on to the next question. Match group A with group B. Okay. Bayet number, Grashof number, Prandtl number, Reynolds number. Very simple question. You know this. You know these numbers already. Okay. Bayet number is ratio of internal thermal resistance to boundary layer thermal resistance. Value is equal to HLC by K. Grashof number is ratio of buoyancy to viscous force. This one. Prandtl number is a very important number in the subject of heat transfer, and it is the ratio of momentum to thermal diffusivities. And Reynolds number is ratio of inertia force to viscous force. Okay, so the answer will be B for this. A will be the answer. Let's move on to the next question. Water flows through a tube of diameter 25 mm at an average velocity of 1 meter per second. The properties of water are given. Rho, mu, K, Prandtl number is also given. Using equation has been given. So the question has been made very simple for you. The convective heat transfer coefficient. It's a very simple question. The equation has already been given. What you have to do is put all these values in this equation and get the answer. You know Nusselt number is equal to HLC by K. The equation is given as 0.023, Reynolds number raised to the power 0.8, Prandtl number raised to the power 0.4. Okay, LC for the tube will be D. When water is flowing, it will be D. Okay, so H D by K is equal to this equation. Okay, I'm putting the values, or you can directly put the values, or you can firstly calculate Reynolds number or Prandtl number, whatever is your choice. So let's calculate Reynolds number first. Reynolds number is rho v d by mu. Rho is 1000, velocity is 1 meter per second. Take care of the units, meter per second. D is 25 mm, that is you have to convert it in meters, 0.025 meter, upon mu is 7.25 into 10 to the power minus 4. Reynolds number is 34482.758. Okay, and Prandtl number is given as 4.85. so put these values here. 0.025 upon K is 0.625 is equal to 0.023. Reynolds number is 34482.758 raised to the power it's 0.8. Prandtl number is 4.85. Prandtl number is raised to the power 0.4. Simple calculation, you get the answer as 4613.666 in watt per meter square Kelvin. We have got the answer in watt per meter square Kelvin. Very simple question, very simple 2 marks question. It was asked in 2014. All you have to do is put the values here. That's it. Next question. For flow of viscous fluid over a flat plate, if the fluid temperature is the same as the plate temperature, the thermal boundary layer is. Okay, try this question before seeing the solution. This question is testing your basic fundamentals, that why the boundary layer, the thermal boundary layer is formed. Okay, so if you have thought about this question, why the thermal boundary layer is formed, what is the basic concept behind the formation of this thermal boundary layer? Thermal boundary layer is developed when there is a difference between the temperatures of plate and the ambient condition. Now it is given that the wall temperature, oh sorry, the plate temperature and the fluid temperature is same, so that means there are no temperature gradients. And when there are no temperature gradients, do you think thermal boundary layer will form? No, it will not be formed at all. So the answer is D, not formed at all. Next question. Okay, again the use of equations. Most of you will think, most of the students will think that it is better to leave this question rather spending time with this question, and they will leave the question without even studying it. Just read the question once. For flow through a pipe of radius r, the velocity and temperature distribution are given. U is given as this. It is, note that it is independent of r, it is a constant, and temperature distribution is also given as this, where C1 and C2 are constants. The bulk mean temperature, the equation is given with um being the mean velocity of flow. The value of Tm is, okay, the equation has been given, urx is given, trx is given, all you have to do is integrate this. Now tell me, is this a difficult question? But most of you will see a lot of equations and will leave the question without even reading it. I mean, just for once read the question, it is a very simple question. Okay, so start putting the values, attempt this question before seeing the solution. Okay, okay, so if you have attempted the question, let me put the values. Okay, so tm is 2 r square, 0 to r, urx is c1, and trx c2 1 minus r cube upon capital R cube. Capital R is constant, okay, it is the radius r which has been given. Okay, so yeah, r dr. Okay, that implies, I'm solving this equation, Tm is equal to 2 um. What will be the value of um being the mean velocity of flow? I told you above that u is constant, it is not dependent upon r, not on x, so um will also be equal to c1. Okay, so 2 c1 r square, 0 to r, c2 I will take outside of integration, and I will multiply this r with this bracket, or minus r raised to the power 4 upon r cube dr in brackets, integrated, Tm is equal to 2c2 by r square upon, this will be r square by 2, and this will be r raised to the power 5 upon 5r cube. This will be from 0 to r. Okay, solve this, you will get Tm is equal to 0.6 c2. A 2 minutes question and students will leave this. You can fetch extra 2 marks, and that means a lot in GATE exam. Next question. In the laminar flow of air, Prandtl number is given as over a heated plate of delta, and okay, laminar flow of air, Prandtl number is given as 0.7 over a heated plate, delta is hydrodynamic boundary layer, and delta T is thermal boundary layer thickness. Okay, yeah. Then, okay, the relation between the two boundary layer thicknesses have been asked. We know that delta upon delta thermal is Prandtl number raised to the power 1 by 3. That implies delta upon delta th is equal to Prandtl number is what? It's given as 0.7 raised to the power 1 by 3. Upon solving this, you will get 0.8879. That is, it is less than 1. When Prandtl number is less than 1, delta is less than delta thermal. So what will be the answer? From the options, we get the answer as C. Okay, if Prandtl number is greater than 1, then delta will be greater than delta thermal, and if Prandtl number is less than equal to 1, then both the boundary layer thicknesses will be equal. This is the beauty of Prandtl number, that it relates the viscous boundary layer with the thermal boundary layer. Okay, the next question is the ratio of momentum diffusivity to thermal diffusivity alpha is called, everyone will know this, that Prandtl number is equal to ratio of momentum diffusivity to thermal diffusivity. That is, it actually relates whether in the boundary layer, whether the rate of momentum transfer will be greater or the rate of heat transfer will be greater, thermal diffusion will be greater. The next question is a fluid, Prandtl number is 1. Okay, so Prandtl number is 1, so I will write delta is equal to delta thermal here only. Prandtl number is 1, that is thickness of viscous boundary layer will be equal to thickness of thermal boundary layer. Temperature is given as 500 Kelvin. Length of the plate is 1.5 meters, and uh, it is maintained at 300 Kelvin. Okay. The velocity of the fluid is 10 meter per second. Assuming kinematic viscosity nu, the value is given as 30 into 10 to the power minus 6 meter square second. Meter square second, take care of the units. The thermal boundary layer thickness in mm at 0.5 meter from the leading edge. Remember, you have to give the answer in mm. Right here that you have to give the answer in mm and not in meters, so that you don't commit the error, because in this question no options have been given. You have to directly fill the answer. Okay, so try to avoid the careless mistakes. Right here that you have to give the answer in mm. Write on your notebook in the side, on the right side, left side, wherever you want to write. Okay, so Prandtl number is 1. We have to find the thermal boundary layer thickness at 0.5 meters. So what we'll do, firstly we have to see that whether at 0.5 meters the flow is laminar or turbulent. So how we can see that? We can see that with the help of Reynolds number, which is rho v d by mu. Okay, kinematic viscosity is rho upon mu, so that will be v d upon nu, or it's rho v l upon mu. For a flat plate, it's rho v l upon mu. So putting the values, v, what is v? Velocity is given as 10, l is given as, l is this 0.5 meters, because you have to find the boundary layer thickness at 0.5 meters. So you have to know that at 0.5 meters what the flow is. So L is 0.5 upon nu is 30 into 10 raised to the power minus 6. When you solve this, Reynolds number will be 1.67 into 10 raised to the power 5, which is less than 5 into 10 raised to the power 5. That means the flow is, yeah, it's laminar. Okay, the flow is laminar. This is the condition, you must know this. Yeah, so for this, delta is equal to 5x upon root rex. Remember this equation, you must have already learned it. Putting the values, 5 into 0.5 upon 1.67 into 10 to the power 5, it is 6.123 into 10 raised to the power minus 3 meters. We have to fill the answer in mm. Okay, be careful. But you have to find the thermal boundary layer, and here you have got the viscous boundary layer. The Prandtl number is 1, so that implies delta is equal to delta thermal, which is 6.123 mm. Okay, fill the answer. 6.123. Take care of the units. I repeat,